hidden layer, and then you just train the output layer. And doing that, it trains way faster. So I don't have a project set up. Hold on, let me just create a new C project. Like I said, haven't streamed for a bit, so I'm just making sure everything's set up. All right. So actually what I'm going to do is I'm going to copy these. I'm going to copy one of these example projects. It's a base because it has a Visual Studio project in it. Now we're just going to rename the project. Also need to go into the text file, rename it in here. And that's how you copy and rename a Visual Studio project. And just open it up. So I'm starting from scratch. I'm going to start by programming a neural net. Do I have a little neural net right here? No, I don't. So I've programmed a bunch of different neural nets, and I've never been completely happy with them. Like, they end up training, but they train way too slow in my opinion, so that's why I'm still searching for new techniques like the extreme learning machine method. Alright, so while Visual Studio loads super slowly, I'm going to create my neuralnet.h. I do the header only way of doing libraries where all I do is have a header and all my code is in the header because I do not care. I do not do C files. It just wastes time in my opinion. The organization is not worth the extra time of creating new file. What the fuck, Visual Studio? God damn it. Can you... No, your trial is expired. Okay, hold on. I guess I gotta sign into my Microsoft account. Was my webcam just lagging? Huh. Seems like Visual Studio is actually making my PC lag. I don't know what happened. Actually, it's a Windows update. Do you want Internet Explorer to remember this password? No. So Visual Studio is actually embedding Internet Explorer to do the logins for the Microsoft account. Jesus Christ. All right. There we go. Man, it's weird. It actually didn't tell me this was a trial when I downloaded it. It just said it was Community Edition. Microsoft are greedy motherfuckers, I'll tell you that. Alright, so let me look at this main.c. What's in that right now? This is just a test for lists, so I'm going to delete that. Date that to 2019. Yeah, I have not worked on my engine for a while, since 2018. I really need to get back into that. So let's get started with the neural net. So this that right there is the MIT license. So first we need this to check if the header has already been included, because it's C. Then we're going to include our header right here, neuralnet.h. All right, type def struct neuralnet. So I'm actually not completely sure how I want to do this because I know it's just going to have a hidden layer. It's only going to have 2 real layers outside of the input. So I'm still not sure how I want to structure this, because normally I do a neural network state object that has all the states, input, hidden, output. But in this case, I might do the hidden and output together. I don't know what happened, but like my PC is stuttering every once in a while. The mouse will freeze and everything will freeze for a few seconds. And it only started happening after this Windows update. I also want to use SSE and AVX at some point, so I probably want to do the biases and weights separately for different layers, just so that there's no so I can align it, because SSE and AVX have to be aligned to 16 or 32 bytes. So, so I'm going to do biases 0, biases 1, weights 0, weights 1. So those are the layer numbers. Biases 1 is the hidden layer biases, weights 1 is the hidden layer weights, 2 is the output. So then we need our structure information. That's the size 1, size 2, size 0. So the size of the input, the size of the hidden, and the size of the output. So we're going to create our new neural net function that initializes the neural net structure. Doing some nice object-oriented programming. This is going to need std int, I believe. Maybe stdio for malloc or something like that. Probably needs std bool too. We'll see. We will see. So I'm not going to do AVX or anything right away. You know what? I shouldn't worry about naming or anything right now. So that'll make it really easy to type out. Hold on. Okay. All right. Oh. Get back in my chair. I've got a really small desk here that my legs barely fit under. Okay. So I guess I'm just going to input all these values on new neural net. Alright, then I need to allocate the weights and biases, and I'm going to do these together in one malloc call. That way the delete neural net can just be like this. All I need to do is free the first pointer because they're combined. So mallocate, memory allocate. How much do I need? First of all, I need size 1 and size 2 biases. Then I need size 0 to 1 weights, and I need size 2 to 1. Okay, there we go. And then each of those are times 4 because they're floats. Oh yeah, so the other thing about this is because you have a fixed hidden layer, you can actually, so the final layer, because you're training with back propagation or just simple adding the errors, it works best with linear rectifier, but because you're not training the hidden layer, you can use anything. You can use sine waves, you can, because the way I'm looking at training it is evolving. So yeah, so actually I should create a delegate function for the activation function. How? Man, I have not written C for a good amount of time. How does this work again? I have this somewhere in my code. In MISC, I think. Yeah, right here. No arc function, neural net activation function. Oh man, it bugs the shit out of me that I did this capital. Where do I use all these? I'm actually gonna go through and name all these. Rename all these because whatever. It's no big deal. Alright. So once this is allocated though, I guess I gotta do one thing at a time. So the activation function takes in a value. Okay, no, yeah, it's bugging the heck out of me that that's different. I'm gonna change that. All right, now I gotta rename these. Oh, I should actually just do find and replace. Oh, I guess that's the last one. I think I can just do replace all here. Yep. Check 2. Nope, that's the last. Oh my god, I got a lot of replacing to do. Oh, I gotta fix something on the timer too. I forgot about that. I gotta put some music on. What am I doing? The fuck is this music? I searched up electro hardstyle. I got this Russian stuff. Oh man, YouTube sucks now. Let's try something else.
To the club, I got like your #1 DJ, always getting the party started. Awesome. Oh, biscuit. What about that? Yeah, you always make me go.
Alright, that's kind of what I'm looking for. That is fucking loud.
I could give you a sky and the light will guide you. Running the wild, I swear I'll find you. Open your mind.
Okay, maybe a bit more quiet. Holy shit, this is loud. Apparently DJ in 2019 just means turning the volume way too fucking high. God damn it.
Put a click house on major. Me and Hat heard I eat booty.
Are you fucking kidding me, Justin Bieber Trap Remix? YouTube is just fucking trolling me at this point, I swear to God. God damn, this is better than all that other shit. I guess we're going with this. Dwarves of the First Age. I don't know what kind of music this is. Oh. It has soundtracks from different games. Oh, okay, I like that. Alright. Alright, you know what? What am I doing? What am I doing? Actually, I'm looking... So what I've been looking for is some nice epic music that really gets me into programming. I don't know what I'm thinking. I know exactly what I need to listen to. Boop, neural net's set up, memory is allocated. Now we need to initialize it. Actually, we're going to program the forward and back propagation first. Wow, the epic background music. That's 2 steps from hell. It's an amazing orchestra music. It's used in a whole bunch of movies. It's great. Actually, I'm gonna, instead of doing input hidden output, I'm gonna have it match up with these. I'm gonna do V0, V1, V2. How long are you programming? Today, I don't know. At least until I get a basic neural net set up, which might not be long, we'll see. Right now I'm rewriting a bunch of stuff that I had in JavaScript before, that I tested in JavaScript. And now I'm converting it over to C where I actually want to use it. Might want to lower this a little bit. Alright. So right now I'm just allocating memory and pointers for the neural net. I mean your program age. I've been programming for like over 10 years now. Yeah, probably like 12 years. Oh, I almost forgot my activation function. Do I want to write the same code twice? I probably do. I wonder if I should store these as a pointer or an array, I mean, so then I can access them through looping here. I mean, technically I can access... Oh wait, I'm an idiot. This is C. I've been doing too much JavaScript. Thank God for unions. What is your favorite game? RuneScape from like the 2006 era. This is how it works, right? I think. Let me test this. I don't hear that. Oh yeah, the music went up. Yeah, part of the issue is YouTube auto balances the music, makes the gain go up and down as the music changes, or sound, and it just kind of makes the levels all over the place. It sucks. I wish there was a way to turn it off. Okay, so here I want to do S1 and I want to see if these values are the same. Sets it to 245. We're going to see if this compiles even. I did this wrong, I think. How am I supposed to do this? Your work amazing, thank you. I definitely spend a lot of time programming. I don't know what's wrong with this. Is it right here? Oh yeah, it's the union. Okay, C union example. Which one is a good one? Except that each data member begins at the exact same location in memory. The data members as structs do not be primitive values. And it doesn't have any example code. God damn it. I haven't used unions for like... Oh, yeah. Okay. I should have realized that. I just need a semicolon there. Wait, where even? Oh. There we go. Zero, yeah, so okay. It's not working. This is why you test stuff first. I think this needs to be a structure. Yes, okay, there we go. Yeah, I do not use unions a lot. See, I'm doing this, but I think what I could just do is, instead of being an idiot like this, I could just do like that. Instead of being stubborn and having to write S1, S2 and both of them separate. I'm a huge minimalist. It's actually an issue. Alright, let me just compile this, make sure. Oh yeah, that's going to compile because neuralnet isn't used. Alright, let's go ahead and write this now. So now I can just do... So forward, this is the main part of the neural net. This propagates the neural network input state forward to the hidden state, then to the output state through the biases and weights. So that's what we're going to program right now. So first of all, we need the... There are two layers we're processing, hidden and output. Jesus Christ, I lower the audio and it just gets louder. It just gets louder. Alright. So, our hidden layer is input, the input layer right here, which is S0. So that's our size, S0. Or, we're doing this in a for loop. This for loop is going to be processing the hidden and output layer. So we actually need to do layer as the input. So that way the hidden will be input and the output will be input the hidden. Then we need the output size, which is layer plus 1. So then our output size is the number of neurons we're processing. So you do a for loop through those neurons right there. And the audio is getting even louder. Holy God, this music is so good. Can't deny it. Alright, so we have our value of our neuron. This starts off as the bias, so we need our array of biases. While we're at it, we'll get our array of weights too. So bias is n. Oh yeah, so I'm going to want to do all of these in an array. I'm just going to do all of this in an array. It just makes it so much easier. Alright, so now I can just do bias layer, weights layer. Alright, so now the value starts out as the bias. We increment the bias pointer when we do that for efficiency. Then we go and we loop through all of the input. So I just realized as well, so the way I do this as well is a lot of people only connect the hidden to the output. I like to connect the output to the hidden and the input because there's no point for it to not also have that input information. You already have that input data. It is a waste not to use it in the output processing. So especially one of the key tests I do, mimicking the triangle wave with the neural network, it is less efficient if you don't connect the output to the input. So I need to add a little check in here that actually does an extra connection. So I'll do this first. So this is just V. We sum the value, which is going to be really simple. Just sum the value of the weight times the input value. So we also need the input array. And I'm going to make this an array too. Yeah, I did not think about this before I designed it. I'm kind of doing a new structure. It actually blows my mind how I turn the volume down and this just manages to get even louder. I think it's reached a peak. And it's just more. It's like neural nets. You just need more neurons. Okay. So the input value is like that. Actually, I'm gonna need to set this each time, so I'll do it right here. Array equals the layer. So there we go. Then we check if the layer is the output layer, we also add the input layer. So then I need another size variable here. So much for orchestra music, though. Alright, so this is going to be size 0. IA is going to be 0. There we go. Alright. So this loops through all of the neurons in the output layer. This initializes the value to the bias, which then adds all of the input values multiplied by the weights, scaled by the weights. Then at the end here, we do the activation function. So if the layer is 1, we are just going to do a linear rectifier activation where we're just going to clamp it between 0 and 1. So I don't know if I want to do that. Probably just going to do it like this with Fmin and Fmax. Clamp it between 0 and 1. And then right here we actually have our custom activation function. So I'm going to provide a linear activation function that does this exact same thing. Just so that people can use if they just want something they can just easily throw in. Alright. So this is just V equals... Yeah, so I should actually save the activation function right here, so I can easily call it ActiveF. Runs our neuron value through the activation function at the end. Then we need our output array, which is state value layer at the index layer plus 1. Then we output our value there, and boom, that's the forward propagation. That is all there is. Right. So now I'm going to do the training that just trains the final output layer. It doesn't train the hidden layer or do any back propagation. which is the key part of how the extreme learning machine learns so fast. The backpropagation actually causes a lot of issues and fighting between the neurons. Yeah, like I said, I haven't actually done this exact structure of a network before. So I'm not sure how I want to make the training function. I think what I'll just do is have the input neural state S, which is needed for the backpropagation, and then so the input error derivative. Okay, I should actually comment this. The error derivative is going to be input in the output layer, because the error derivative is your target minus the output. It's going to be, you're going to store that data in the output value because it's just going to be subtracting. So all right. I'm going to separate these. Allocate new network object. Oh, I forgot to actually initialize this value for the neural state to the network object. Alright, forward, propagate, input state, through neural net N to output state. That's 2. There we go, okay. Train output layer of neural net N using derivative / error in output state v2. Alright, that actually sums basically everything you need to know. So then this is just training the output layer. So that's just going to be the, I'm going to need the input size again, which will be S1, then the actually, so because it's the output layer and I have the extra part where it's connected to the input as well, I'm going to need an extra part there. So I'm going to need size 0, 1 is NS1, output size is NS2, okay. So then we're going to do just like we do here, move through the output neurons that we're training. Alright, so we also need our float data from the state. So we're going to need our error, which is, like we said, SV2. Then we're also going to need our input state, which is SV1. And actually there's 2 inputs, which is what I was talking about before there. We input the input, it's V0, and we input the hidden, it's V1. Okay, it's bugging the shit out of my OCD that this 2 is, it's not in the proper order. Will not do, okay. Alright, so how do I want to do this? Do I want to clamp? Oh yeah, I also need the biases and the weights to train. Alright, so first of all, have our error. Oh yeah, so we also have a training rate or learning rate. So we multiply the error by this rate. We add this error to the bias that does the training. Then we need to loop through the inputs and do that training. Alright, so we actually do it in the backwards order, so I actually have to do V1 first. So then for this training, you do error times the state, the input state. So in this case, the input state is V1. And actually, yeah, so this is one of those cases I'm actually going to need to initialize it each time. So error is the only one that I need to keep track of through the whole loop. So that needs to be reset each time. So if anyone's familiar with the Fourier transformation, this is nearly the exact same concept. You are multiplying the input state by your target output state and summing all of these values and averaging them gives you the multipliers or frequencies you're looking for. Math is amazing. It also works really well if you replace layers of the neural net with the Fourier transform, or you input Fourier transform results to the neural network. It makes processing, I mean, anyone who's done audio processing is already aware of this, that you basically need to run the data through the Fourier transform first. But it actually works for everything. It works for image processing, it works for text processing. Okay. So that trains the output to hidden. Now this is going to train the input to output. Boom. There's our training. That lined up with the music. That was great. Alright, so there's our forward propagation. There's our training. No back propagation. This is a special neural net. So instead of back propagating to train the hidden layer, we're going to use good old evolution. So this is going to be the interesting part, is finding the best way to evolve the hidden layer. So we're going to begin setting up a test now. I'm going to be surprised if this compiles with just stdint, because I don't think stdint gives access to malocate, but maybe I'll do stdlib just to be safe, or string.h. We'll see. If I'm doing SSE and AVX, actually, it'll eventually, I'll have to include the header for that, and it'll include all the stuff. Alright, let me just make sure that is everything right. Yeah, so... Okay. The hard part now is going to be finding the best way to initialize the neural network. I have a lot of ideas for how to do that. One of my theories is, so there's obviously just brute force evolution where you just set it to a whole bunch of random values and just try over and over again. But what I want to do is create some sort of genetic framework. I'm thinking just arrays of values of probability Okay, I have two ideas. I have one of discrete values that each have their own probabilities, so you have a probability distribution of each weight or bias being a certain value. So that would allow, over time, the networks to find, I don't know how to describe them, they would find the best areas to have their weights and biases. Then the other one is that instead of doing a probability distribution, you have a min, max, and average of the randomly generated states. Anyways, I should start just working on the tests, because talking about this, the real thing is writing out code that works. It doesn't matter how much I talk about it. There's no code. Alright, so what I want to do though is I want to make some sort of framework. Or not framework, but I want to set up some, I'm going to be doing 3 or so different tests for the neural network. I'm going to be doing the triangle wave test. Holy shit, this is getting so loud. It's actually impressive how loud they make some of their music. I'm going to be making like 3 different tests. The first one is just going to be a simple triangle wave, mimicking a triangle wave. Then it's going to be trying to generate text with a recurrent neural net model. Then it's going to be playing tic-tac-toe and learning with reinforcement learning in a recurrent network model, which is like the playing a game. That's like the top goal. I'm definitely not going to get that done today. Hopefully I'll get the triangle wave test done. Pretty sure I will. But I want to set up the system so that I can test it with different neural nets if I want to change parts of this to see if certain techniques work better. So I guess I'll actually just design it all here with some set functions that are called. Alright, so I'm going to do the tests using defines, test triangle wave. So like if this is defined, it's going to do a triangle wave test. Alright. So the first test I'm going to do is I'm going to test brute force evolution versus one of these genetic models. I might just do a simple one of brute force mixed with mixing neural nets. We'll see. I want to get actual benchmarks of how much faster it is to use some genetic algorithms than brute force evolution. So how do I want to write out this test? So first of all, we'll write our triangle wave. So this is a triangle wave. I believe. So it goes up, value goes up at the halfway part, it's 0.5. And then at the halfway mark it starts going down again to 0 at 1. So this is actually a neural network if you look at it. This is the input is one input value v. Then if you think about it, the output neuron has an input. One of the connections is to the input v with a weight of 2. Then another one is a hidden layer neuron with an activation function of linear rectifier max 0. That one has an input weight of ×4 and then a bias, or an input weight of -4 and a bias of 2. Then that has an input weight of -1. So this is why I believe it's such a good test for neural nets, because it's actually a neural net itself if you look at it. So the neural net realistically should be able to match this perfectly if you actually have a method that trains to it. And that's part of my issue with the backpropagation training methods. I have never found a method with Adagrad or anything that actually manages to reach this 100%. It does after millions of iterations, and I really think that millions is way too many for something like a triangle wave. So that's why I'm looking at extreme learning machines that actually learn very quickly. So how am I going to test the different neural net models? Whatever. We're going to initialize our neural net, new neural net, input size of 1, hidden size of 1, output size of 1. Match up perfectly with this. Then we also need our activation function. It's just going to be one of these linear activation functions. Maybe. Yeah, actually, okay, that'll work. Neural net activation linear. Alright, so then we're going to go through tons of iterations to see how good a neural net we get after evolving for a set number of iterations. We're also going to benchmark how long that takes. So I need system.h for the time now function, that's why I'm including that. Alright, so that'll measure the time. Okay. So the first thing we're going to need to do is randomly initialize our neural network. So how am I going to do this? So this is where I'm probably going to do the evolution and all of that. Brute force. Brute force evolved. These are going to be all the different options for testing. Allow to switch between different tests pretty simply. So set up the neural network, then here we'll run the tests. So there's going to be 2 iterations. There's going to be generation iterations, and there's going to be training iterations. So the final value will be these multiplied by each other. So that's going to be like 1,000,000. Oh crap. Oh, okay, that's a good amount. That's a good amount. Now the music's getting more quiet. Oh man. Alright. So I need a range for setting up the evolve, the weights and biases. Alright. So first of all, I'm randomly generating this. I'm going to need RNG. So I'm going to include my RNG.h. We're going to initialize RNG here at the beginning. I'll initialize it to the time. Alright. So now we need to loop through all the weights and biases to generate the random values. So we want all of the size values. Or do I? Let me see, maybe. Let me try just looping through the layers first. Yeah, kind of. Yeah, actually, because I'll want to initialize one layer differently later on. So I should do it this way. Okay. So RNG float. So for the hidden layer, where do I want to generate the biases between? Probably bias range 10, weight range 5. Yeah, we'll do 5. 5 is probably good. The lower we make it, the faster it'll get for the triangle wave, but the difference is it'll be a different range for each. This is the whole idea of the evolution too, is you can actually evolve the range to fit whatever you're working on. There's some things where you actually want a higher range than others. Just like how the triangle wave works well with a low range, there's things that need a big range. Alright, so this randomly generates the weights and biases between the set range. For the hidden layer. Now we need to do it for the output layer. So now, because we're actually training the output layer, we might want to do this differently. I don't know. So also because there's two inputs here. Yeah, I'm just going to try this to start, and then maybe I'll lower it. See how well it does. Alright, so that sets it up. Oh yeah, we also need a neural network state. Okay. I think we're actually ready to do the training now. Training iterations. Do I want to... Oh, do I want to do dropout? So, as you're training through it, you can step through each... You can step at discrete values through the function you're looking for. But that doesn't work as well as if you generate random points on it that are like blue noise, evenly distributed, like blue noise. The issue is, okay, and then you can get it even better by dropping out half of those random points. I do not know how dropout actually, it makes no sense to me how dropping out half of the data each batch you train it makes it better, but it does. So dropout would be generating an array of grid points and randomly moving them around so they're fairly evenly distributed. So yeah, I'm going to split training into segments. Actually, how do I want to do this? Maybe I should use quasi-random point sampling. Let me think about this. This would actually be a good time to use it, wouldn't it? Not random. Ends up being evenly distributed. Let me actually, the code for the R2 version right here. But R1 should be pretty easy. I think I linked to the article. Yeah, extreme learning. Unreasonable effectiveness of quasi-random sequences. Okay, so I need R1. Value is 1.6. Yeah, so in one dimension, pseudocode is this. Alright. So what this is going to do is this is going to do quasi-random sampling for this triangle wave function. So this is really good because it's going to sample evenly across the space. But it's still going to be random enough that it's not sampling the same points over and over again. So that is a key part. Alright, so I need to, let me just implement R1. So how is this? Wait, mod 1? Oh, okay, it's in float, that's fract. I was looking at that as like integers for a second, I'm like, wait, what? 0.5f plus 1 divided by this. Wait, is that... Oh, times n, which is t, and then mod 1, so... fract. Wait, is f fract a thing in C? There isn't a fract, isn't there? You just do f mod 1, eh? Oh, mod f. I don't know why I wouldn't just use f mod. Just like that. Okay. So that gives us our x to sample on the triangle wave in the neural net. So we run the neural net now. Set the input state value to the x. We run the neural net forward. Neural state. We run the triangle wave to give us our target. And then we compare, or to get our error derivative, we go to the last layer and we subtract that from the target. So for example, if our target is 1 and our state is 0, it tells us we need to go up by 1 to reach 1 from 0. And then using that data is how it trains. It tells the neurons they need to either go up or down more. So when you train like that, yeah, I also need a learning rate. So define that. I'm just going to do 0.1. Alright. Then how do I want to measure the accuracy of this when it finishes? So what this is going to do is this is going to go through and find the most accurate with the minimum loss. So after this, I guess I'm going to... Oh man, I could actually calculate this mostly right here. It's just how would I average this? I mean, I think maybe like smooth max. I think smooth max might work here. Or smooth min. What is smooth? What's the code for smooth max again? Oh yeah, log sum of exponents. I think that's it. Alright, one sec, I gotta take care of my cat. Listen to the awesome music. Alright, hold on. Let me see what the result of this would be. JavaScript is so good for just testing out stuff like this in the console. Okay, that is not working. Just keeps going up. Alright, let me do a loss. Oh, it's literally just log loss. No, never mind. That's not what I'm looking for. Alright. Alright. So what I'm going to do is loss. You know what? I'm going to do average loss throughout the whole thing. I'm going to try doing that. Actually, no. It should be ending loss, just to be, like, fair. So yeah, I am gonna calculate loss at the end, because so to do that, I'm just gonna do 10 iterations through. Hell yeah. Alright, so now that adds up positive loss values. Divide that by 10 and you've got the average loss. So then I want to calculate the min loss. Then I'm going to output that. There we go. Output min loss. Alright. I'm betting this is going to crash, but you know what? Let's run and test it. Let's point destructor union. Wait, what part is that? Forward propagation. What's happening here? NS. Left of S. Oh, in this, N becomes that. Okay, so I need to make either change this. I should also work. Oh, that's neuralnet instead of neural state. I is undeclared. S is not a member of neural state. Oh, it's V. There we go. Alright, let's see if this crashes. Min loss of -1 executed 1,000,000 iterations in 146 milliseconds. I should actually do this. Executed iterations in times training iterations. Loss. Wait. Why is this -1? If this is absolute value, huh? Let me try this again. Yeah, average loss 30, min loss of -1. What is happening there? Even the 30 times 0.1 should be 3. Why is F min here? Why is F min showing that? Huh. What is happening with F min? Oh, I think it's G. It's the G output tag I'm using. No, it's not that. What the hell is happening with F min? Oh my god, is it actually F min F? What is even happening here? How is F min 4.5 outputting 0? What in the... Okay, there's... I think it's actually overwriting memory and it's just not crashing somewhere. That's my only explanation for why F min wouldn't work. Yeah, no, it's what the hell? Microsoft Visual Studio F min bugged. like, this actually makes no sense. What if I convert it to an integer first? Just to make sure it's not the printf. No, it's still -1. It goes to -1. What the hell? Holy shit, what's happening? This is actually ridiculous. Is the compiler bugged, or I don't have a debugger on here besides Visual Studio Debugger sucks. What are my compilation options? Do I have optimization on? I do. Try something. Oh my god, if it's the compiler optimizing it out, no. That makes it, oh god, no. If this is a bug that's just like a straight up bug that there's no solution for, I am dumbfounded. Microsoft Visual Studio fmin doesn't work. I don't overwrite fmin anywhere, do I? If not define min max. No, yeah, so wait. Wait. Include math.h. Oh my god, it's... What the fuck, C? So, I didn't include math.h, which is the header for fmin and fmax, but it didn't throw any errors. Instead, it just didn't work. Like, actually, hold on. I need to post this on Discord. I have never seen something like this before in C. Alright, that is actually ridiculous. That is ridiculous. This is the type of shit that makes me hate JavaScript. Is you'll compile something like this, and it won't give you any errors even though it's wrong. So this should have thrown an error. Me not having math.h and trying to use functions from it fmin, for some reason Visual Studio didn't throw any compiler errors. Instead, it still compiled my program and just made all the math functions return -1. Which is absolutely crazy. I don't know, like, that's, alright. Sometimes I really wonder what goes on at Microsoft. Alright. The loss is not changing, which means it's not training. That's okay though, at least it's running. Alright, min loss 0.7. Alright, so let's try and do it without training. Yeah, so it should be doing different minimum loss values each time if it really is randomly setting up the network, but it's not. So this leads me to believe there's something wrong with it. Oh, I'm setting weight 1 here and weight 0 is being set. That could be it. RNG, oh, I'm not initializing RNG. It's doing the exact same thing each time. Oh. There we go. Yeah, so it trains to like 6. It's 6. Yeah, so I wonder what the odds are. The odds probably are not good of finding the actual configuration with a weight and bias range of 10. Let me try this. 0 training iterations. We'll just do 1,000,000 generation iterations. So it does not get any better than 0.6. That is worrying. That makes me wonder. Because it should be able to maybe if I remove the fmin from here. Oh yeah, that made it improve, but it's still only getting like 0.4. Yeah, I want to actually see what the neural net is outputting. Probably going to have it output the best values. I think. Why is this going wrong though? It should, after 1,000,000 iterations, at least not be as constant as 0.4. It should be finding better amounts than 0.4. Unless the neural net isn't running properly, that is always a possibility. Hmm. Yeah, so I'm going to store these test values. Then I'm going to output the output values here. Alright, I want to see what it's outputting. 0.5, 0.6, 1.4. Yeah, so all of the first ones are 0 for some reason. That is worrying. Or not worrying, but something is obviously broken because it should be more than 0. And it's being basically the exact same 1.9 each time it executes. Which is really weird when the weights and biases are so different. Oh, I'm not allocating enough space. I'm surprised this didn't crash. This is also supposed to be size 0 times size 2. Okay, so that still didn't fix it. I don't know why these values are so close if the range is supposed to be... Let me test this random number generator and make sure it's working. -5.8, -5, +5, -1.9, -9. Yeah, it's random. Alright, something is definitely executing wrong, I think. Let me try something else. Oops, I closed the terminal. Oh yeah, so there we go. Okay, so it's the bias. It's interesting how it's generating nearly identical numbers even though the random numbers are different. Yeah, I really feel like something is wrong with maybe with the setup here. Hmm. Yeah, so this doesn't make sense actually. With the weight ranges being both negative and positive, these values should show up as zeros sometimes as they get clamped. They are not though, which means it's never showing up as negative for some reason. For some reason. Alright, I'm going to create a function that prints floats. Just so that I can easily throw the neural net biases into here, or weights, and output them. So like right here, I could do printfs, print 10 floats. Alright, so I also want to print the neural net. So I'll print the biases from there, which should print out all of the weights and everything. So let me think about that. 2 biases, 3 weights, so that's 5. Yeah, so you can see there the first bias is actually negative. The first weight is negative 2. Oh, they're insanely small values. E negative 30. That's not making much sense. If the values are so small, I'm actually thinking it might be something with the execution. Oh my god, I'm outputting it right here. Wait. No, that's correct. Never mind. Yeah, I actually don't know what's going wrong here. Maybe it's not outputting all of them. No, that is all of them. First weight is 0.9. Wait. Yeah, so if the output is negative, and even the bias is just a small value, then it makes no sense that the output here is all the way up at 1.9 or 1. Alright, so something's definitely wrong. Or wrong with the execution. I'll try doing no activation function. Weight times input. Alright, let me try outputting just the output weight. .9, 0.5. Negative 0.5, 0.6. 0.5, negative 0.3. Both negative and small values, and it still outputs a positive value. So, yeah, it makes me wonder if I'm just reading these values wrong. I don't think M's could be my mem copy right here. I don't think so though. It's copying from the temporary to the test, outputting the test. Maybe I need to do a pointer. We'll see. Visual Studio likes to do some weird shit sometimes. Nope. Somehow this ended up negative as well. That doesn't make any sense. So we're going to take all this away. We're going to do one iteration. And I'm going to output the values for that iteration as well as the weights and biases. So this is the hidden layer value, and that's the output layer value. Yeah, so it was actually just my output. Huh. Wait, what's going wrong there? No. Oh my god, wait, it's right now. What? Does it bug out if I increase the generations? Maybe it was never bugging out. No, now it's never negative. Oh, because the minimum ones are never negative. Oh my god, it was working fine the whole time. It just worked really badly. I should have realized. Alright, so we're gonna add the rectifiers now. So all that is setting up correctly. Okay. Still though, it should be finding better values than this, I believe. Let me make sure this is even possible. Let me think about this. Maybe I messed something up. So the triangle wave have a weight of 2. It's the range of 2. Oh, okay, so I need a range of 4 for this multiplier. So actually, how would this be? You know what, as a test, I'm going to set up the neural net manually. Set all the weights and biases. I'm going to try and do what I said, where set the weights and biases to these exact values, and that's how I'll check and make sure everything's working. So the first bias is 2. The first weight is -4. Oh, wait, this isn't a triangle wave. It's supposed to be -2. Oh. Well, that could explain it. So then that has a bias of 0. That has a bias of 1, or actually -1. That has a bias of 2. Alright, so this should be perfect as far as I'm aware. Min loss 0, it works! Hell yeah. Okay. I'm gonna go check on my cat. I'll be right back. Glad that everything works properly here, so I'm gonna go ahead and actually do the tests then. Or actually, while I stand up, I should do one of these. The evolution takes a very long time. It's just brute force. So what I'm going to do is I'm going to initialize the evolution. Set up everything I need. Set up the range. So if I run this, yeah, it actually gets pretty close now. Yeah, it's actually decent for evolution. Okay. You know what's funny? I was saying how the back propagation does it in millions of iterations and barely gets it perfect. The evolution is performing basically the same as the back propagation. Alright, so I'm going to set this to like 1 billion. We're going to do a long execution. See how accurate it gets. I'll be right back. I'm going to check on my cat, get some water. See how good this does when I get back. Alright, 50 seconds to a loss of 3.7%. Should actually convert this. Alright, so the next thing is we're going to try training this. So as well as evolving it, we're going to apply a little bit of training iterations to see if we can push it a bit closer. Minimum loss of 5.8%. How do you do C printf include percent? Oh, 2 of them. Alright, there we go. So yeah, loss of like 5%. Evolution has major diminishing returns. So running it 10 times as long only gave us half as much loss, which is not worth it. So that's why we're going to try to improve it a little bit with training rate. So we're going to add 10 training iterations, see if it makes it better or worse. 2.4%. That is amazing. So we got the better training rate than the 50 seconds in twice the time. So we got the same benefit as before with 20 times the speed. It is still semi-random though. It's not 2 every time. So we're gonna now mess with the hyperparameters, the learning rate. We'll lower the learning rate a bit, see if that makes it better or worse. Mess with the iterations. Okay. Lower learning rate is worse, unless we raise the iterations. We'll try both. 50 training iterations, or maybe 100. And we'll try something different besides R2 point sampling as well. There's so many things you can test with neural networks, so many areas apply. It's crazy. Alright, so let's lower the generation iterations to compensate. Increase training iterations so it ends up being the same, 715. 1.5% loss. PogChamp. That is amazing. 0.7% loss. That is really good loss. So that is 0.7 out of 100% is on average different than our triangle wave function that our neural network is mimicking. And it trains in 10 million iterations in 1717 milliseconds, which could be better. Could be better. We got 0.46%. Oh shit. Getting even better. So now I'm going to try messing with these options. I'm going to try lowering the learning rate a bit. Like I said, I'm going to try without the R2 or R1 point sampling. Alright, no, yeah, that made it worse. So yeah, the 0.1 learning rate, very good learning rate. Maybe even increasing it to 0.2. We'll see. Let's try it. Oh my god, that made it even better. 0.3%, 0.28%, 0.21%. Holy cow, that's really good. I'm really happy with that just right away. Awesome. Alright. So this is the R1 point sampling, quasi-random, I don't have the web page open anymore, quasi-random point sampling. What would I do instead of this? Just random sampling? Just completely white noise sampling? Let's try that. I think it's going to be way worse. 0.3%, 0.25%. It's basically the same. You know what? It is basically the same. I actually think it might be a little bit better. Let's compare them. I should also do dropout. That's probably the next thing I'll do, is I'll compare these to dropout. So they actually seem nearly identical. I guess it's just the, I think R1 is a bit better. But yeah, we'll try dropout next, which is where instead of random sampling the points, well, you do random sample them, you generate like a hat of points, and then you randomly pick the points out of the hat, but you only pick half the points. That's the key part of dropout, is you drop out half of your sample points in your bin or hat. I don't know how that improves it, but it does. So that's what we're going to do next. My cat's being really annoying right now, so I gotta go check on him again. He's a really old cat. He has one eye, so I really need to take care of him. So I'm sorry about this, but alright, let's add dropout. Alright. So we need our list, our bin, our hat. So this is going to hold our sample points, our floating point samples. So it's size of float, which is 4 bytes. So we create this new list. So what we're going to do is when the hat is empty or the length is 0, we're going to generate a new hat, random sample points. I would love to do something like blue noise sampling or something here. Like I maybe should base it off of this R2 sampling, but what I think I'm going to do is I'm going to do randomly offset points. So I don't know if I'm going to do a constant jitter on them, because that would make them evenly spaced. Yes, I am going to do a jitter. Alright, so I'm going to need to choose the number of segments to do for this. Let's do 10 segments, just like how I do here. Alright. So then the jitter is equal to 1 divided by the segments. So now we're going to add our segment points to the hat. So then right here we're going to randomly pick those points out of the hat. And right here I'm just going to comment out the R1 sampling, so we're not going to need it anymore. Alright, so our X value is I divided by segments plus the jitter. Add that to the hat. Add all those to the hat at least. So now hat's length is full again. Our R1X is going to be taken from the list. So need to generate a random list point, a random list index. Then the R1X is equal to that. And then we remove that. Let me just check my list functions. I don't know if it's remove add in this. I've been doing way too much JavaScript. Oh yeah, it's remove add. Okay, awesome. Oh yeah, what does doing it fast do? Downside is it changes the order of the list. I forgot I added this. So this keeps the order by moving everything in the list down. What does this do? The index moves the memory to the index from above. Oh, so it moved the top one down to the bottom one. Oh, okay. I should just do that. It actually doesn't matter here. Okay. Awesome. So this picks random points out of the hat. This is just picking random points. This isn't doing dropout yet. Wait. Actual parameter is not a pointer. Where do I have add_m? I don't think I have add_m anywhere, do I? Oh, did it not save? Actual parameter is not a pointer. Oh my god, yeah. This is C, everything's a pointer. Rgen, undeclared identifier. R1I, undeclared identifier. RLI. Okay, here we go. Alright, so this just picks random points out of a hat. It doesn't actually do dropout. We're going to see if that works any better or more consistent. Still has the same 0.3%. I'm already super happy with this 0.3%. Like, this already is basically as fast as the back propagation was, and it's using evolution, which is incredible. Because evolution is way more flexible than back propagation, I would like to say. Evolution is a universal learning method. It is the brute force way of doing things. So yeah, this is alright. It's actually basically this. Holy shit, 0.01%? That was actually the best one we've ever got. 0.01% is basically perfect. I reckon if we kept training that, it would be perfect. So this is the other thing. In an actual intelligent system that you program, you won't be doing this you at least shouldn't do this very simple method I have of just doing 100 fixed training iterations. You should have some intelligent conditions that's going, okay, if it's this accurate, if the neural network is like our most accurate one yet, then we should spend extra time training it to make it even more accurate, because you've already invested that time getting to the point. It's worth it to add. But see, that stuff is complicated. That is the hyperparameters I'm talking about, where even just changing those values little bits can have huge effects, which is really hard for you to figure out, and that's why evolution, just brute force trying different variables, is amazing, because you can get through that. Anyways, let's do dropout now. So instead of just going through the hat, to do dropout, we have to go halfway through the hat. So if the hat has less than half the segments in them, we're going to redo the hat. So empty the hat is setting the length to 0. So let's try this. 0.19, 0.14, 0.4, 0.58, 0.6, 0.5, 0.29. This actually seems worse than the R1. No, yeah, this is... This is actually performing worse. That's super interesting. Let me see if my remove at fast is affecting anything. It could be. Let me just check this. Hat.length smaller than segments divided by 2. So I'm going to try doing a different jitter on each one. .39, 0.52, 0.1, 0.48, 0.6. That does seem a bit better. 0.2. I think what I should do is do a heck of a load of iterations. Do more training so that I can test just the training. So I'm going to do 1 generation. We'll do 10,000 training iterations. That should give us basically the maximum that we can train. So yeah, that one was alright. 16%. Yeah, this is hard to test because it's inherently random. So like, comparing it to this R1 point sampling, I actually think the R1 point sampling ends up being better. 27%, 4%. Yeah, R1 point sampling is even better. The unreasonable effectiveness of quasi-random point sampling. Alright. I am actually super happy with this. So I'm not going to do dropout or any complicated training method with a hat or anything. I'm just going to do R1 quasi-random point sampling because that works great. I am super happy with this. Okay, I forgot to remove. There we go. So right now it's executing in like, actually what do I have the options set to? 3 million. Oh man, 0.07% in 7 seconds. So it's mimicking it's basically mimicking the triangle function perfectly at this point. That's amazing. It's doing it super quickly. I think part of the overhead with this is it's such a slow neural network too. Like, it's such a small neural net that a lot of the actual instructions are just function calls for the neural net. Like, look at this, training to 1%. accuracy in 8 milliseconds. 4%, 0.5%, 3%. That's really good. All right, I am very happy with that. So the next thing, so this is the brute force evolution model. The next thing is going to be the genetic evolution model. So we're going to find a way to improve, because the core of this is still the generations, evolving different generations of the neural networks and finding which ones are the best. The training isn't the key part. The training just pushes the neural nets a little bit more towards their goal, and it can actually result in you flying past your goal and getting even worse. So training isn't everything. Training can also be the end of the neural network and basically make the neural network function way worse. So that's why we are really going to be focusing on improving the evolution generations, and that is going to be using genetics. So that, I was talking about this a bit at the beginning. There are many different ways to do this, and that's what I'm going to be doing. I'm going to be trying different ways, and I'm going to be seeing which ones function the best. My first one is probably just going to be average, min, and max of each. Instead of randomly generating each weight and bias, I'm going to combine them with the previous best network. So it's basically going to base the weights and biases off what already is working well, with little mutations here and there. The other model is to let each neural net also have a genetic blueprint that basically has the average or the min and max that each weight and bias can be generated to. And then instead of mixing weight and biases when you combine them, you combine their min and max weight biases and then randomly generate from those. So the genetics are more like the design of the programming than the actual programming themselves. The programming for the programming. Anyways, I wonder if I can get this working perfectly. I'm wondering if it's the training, the learning rate. Like I might want to actually make the learning rate go down as it trains, so that way the loss I actually think I can improve it by having the training rate go down over time, so it kind of hones in on an accuracy. So I'm going to try doing a dynamic learning rate right here. So down here in the training, instead of the fixed learning rate, so I can either make it based off of this difference. I can do like absolute value, difference here, times however much I want the learning rate to be. I could take the average of this so it's much smoother. We'll try this to begin. Yeah, so that behaved worse. Alright, so 2.7% for... So we get 2.7% for the dynamic learning rate. We get 1%, sub 1% for the fixed learning rate. The fixed learning rate is way better. Should actually find the best learning rate for the iterations as well. Still seems like 0.1, actually 0.2, the higher value is actually the best, so I guess I'm just going to stick with that. So I should have something that's actually checking how well it's training the network, and if the network is doing bad, it just shouldn't train it. Like, really, yeah. It's a waste to just boost the training iterations for these networks that aren't, So I might do, like, dynamic training iterations. Still working super good though, sub 1%. I want to push how accurate I can get this. Does pushing the training rate up past this help that much? 0.1%, it does, so that's basically everything. This point, I'm guessing, is higher training iterations. This should be sub 0.01% or sub 0.1%. We'll see. Should take like 50 seconds. It should be done soon. We'll see. So I wonder if I want to scale down the training iterations for the worst performing networks. That's like, it's probably a good idea to only put in the training for the ones that are worth it, right? Like, I don't know. I'll try it. Oh my god, 0.002%, 60 seconds. That's obviously really slow, but like, that makes me really happy. It just keeps training. So let's see if I can improve this. If I can improve on these training iterations. If I can somehow detect, if I can put some threshold where it says that training is no longer worth it. Yeah, maybe I should do the max loss over a certain period of time. I don't know, because of the way the quasi-random point sequence works, it won't be able to measure it correctly unless I exit out and do this measurement right here. Like, unless the training iteration is based off of this. Maybe I should just keep training until it's no longer training anymore. Maybe if I measure how much it's learning, and then I stop learning when it stops learning, that is logical. Alright, hold on. Just gotta check Discord. Alright. I will be right back. After I come back, we will try and improve the training. No promises. If not, we're going to move on to genetic evolution. Damn! This music is loud. Alright. Yeah, see, this is hard because it could just get way better from training. I think the fixed training iterations is probably still really good. I'm gonna move on to the genetic evolution, I think. I don't know. I'm pretty happy with this though. I honestly did not think this brute force evolution was gonna work this well. I've actually got to go do some stuff outside, and it looks like it's going to rain. So I'm going to go and I'm going to get that done. And then I wasn't planning on going and streaming this afternoon, but I think I might continue this neuralnet streaming throughout the afternoon. I really love this stuff anyways, so it makes sense that I just keep doing it. I've been meaning to do this for so long. Now that I'm doing it, I may as well just get all these tests done. Like I said, I have other tests planned too, like a recurrent text generating neural net. Do you have a schedule? No. I was streaming over the summer, and now it's back into like the school season and stuff, and it's really busy. So I don't know. I'm trying to stream. We'll see. We'll see. I'm trying to get back into it. I've done streams the past 2 days. I can guarantee I'll at least have a stream once a week on the weekend. Like every weekend I at least do a stream. Other than that, I normally stream in the morning around this time from like 7 to 12, and then I stream at night from like 7 to 12 p.m. So yeah, I'm going to be continuing this stream in like, let's say like 2 to 3 hours, like 1 or 2 p.m. in the afternoon EST, if anyone's interested in that. We're going to do genetic evolution. So, see how that works. Thanks for the follow, guys. Larry Chen, Angry Little Hamster. But yeah, I would love if you guys join me later this afternoon. If not, that's fine. I hope you check it out another time. Thanks so much for checking out the stream. I'll see you guys later. I hope you have as much fun programming neural nets as I do.